Space weather. How solar storms affect Earth and space travel. 1. Introduction. Space weather refers to the environmental conditions in space that can influence both the Earth and human activities in space. At the heart of space weather are phenomena originating from the sun, such as solar storms, which can have profound effects on our planet and our ventures beyond it. Understanding these solar events is crucial for safeguarding technology, infrastructure, and human health. Definition of space weather. Space weather encompasses a variety of phenomena caused by solar activity, including solar flares, coronal mass ejections, CMEs, and solar energetic particle (SEP) events. These phenomena arise from the complex magnetic interactions within the sun and can lead to significant fluctuations in the solar wind, streams of charged particles released from the sun's atmosphere. When these charged particles interact with the Earth's magnetic field and atmosphere, they can create a range of effects that influence both natural systems and human-made technologies. Importance of studying solar storms. The study of solar storms is essential for several reasons. Technological vulnerability. Modern society relies heavily on technology, including satellites for communication, navigation, and weather forecasting. Solar storms can disrupt these systems, leading to communication blackouts or navigation errors. For instance, a severe solar storm in 1989 knocked out power for millions in Quebec, Canada, demonstrating the potential for widespread disruption. Human safety. As space exploration increases, understanding solar storms becomes critical for the safety of astronauts. Spacecraft and astronauts outside of Earth's protective atmosphere are exposed to higher levels of radiation during solar storms, which can pose serious health risks. Environmental impact. Solar storms can also affect the Earth's atmosphere and natural phenomena. For example, they can enhance auroras, northern and southern lights, and impact weather patterns, although the latter is an area of ongoing research. Economic implications. The financial impact of solar storms can be significant. Disruptions to power grids, communication systems, and navigation can lead to substantial economic losses. Assessing and mitigating these risks is vital for national security and economic stability. Historical context. The historical context of solar storms reveals their long-standing impact on Earth and human activities. One of the most notable events occurred in 1859, known as the Carrington event. This massive solar storm caused widespread telegraph outages and produced beautiful auroras seen as far south as the Caribbean. If a similar event were to occur today, the consequences could be exponentially more severe due to our dependence on technology. Current research and future directions. As space weather becomes an increasingly important field of study, researchers are developing advanced models and monitoring systems to predict solar activity. Initiatives like the Solar Dynamics Observatory (SDO) and the Advanced Composition Explorer (ACE) have provided valuable data that enhance our understanding of solar behavior. Ongoing research aims to improve predictive capabilities, enabling timely warnings for solar storms. Moreover, as humanity sets its sights on Mars and beyond, understanding space weather will be critical for the future of space exploration. Developing effective shielding for spacecraft and habitats on other planets will be essential to protect astronauts from solar radiation. Conclusion. In conclusion, the study of space weather, particularly solar storms, is of paramount importance in our increasingly technology-driven society. By understanding the mechanisms and effects of solar storms, we can better prepare for their impacts on Earth and safeguard our ventures into space. As we continue to explore the cosmos, the insights gained from studying space weather will play a crucial role in ensuring the safety and success of future missions. The ongoing research and collaboration in this field will be vital for mitigating risks and harnessing the benefits of solar activity. 2. Understanding solar storms. Solar storms are significant events produced by the sun that can have far-reaching impacts on both Earth and space travel. These storms arise from complex magnetic interactions within the sun, leading to various phenomena that can disrupt technological systems and pose risks to human health. Understanding the nature, types, and mechanisms of solar storms is essential for preparing for their effects. What are solar storms? Solar storms are disturbances in the solar atmosphere that release energy and charged particles into space. They are primarily caused by the sun's magnetic field, which is generated by the movement of electrically charged plasma within its interior. This magnetic field can become twisted and tangled due to the sun's rotation and convection processes, leading to explosive releases of energy. The most common types of solar storms include solar flares, coronal mass ejections, CMEs, and high-speed solar wind. Each of these phenomena has distinct characteristics and implications for Earth and space. Types of solar storms. Solar flares. Solar flares are intense bursts of radiation and energy that occur when the sun's magnetic fields realign. These flares can release vast amounts of energy in the form of X-rays and ultraviolet radiation. They typically last from a few minutes to several hours. Solar flares can disrupt radio communications, GPS signals, and even pose radiation risks to astronauts in space. Coronal mass ejections, CMEs. CMEs are massive bursts of solar wind and magnetic fields rising above the solar corona or being released into space. They can contain billions of tons of plasma and travel at speeds of up to 3,000 kilometers per second. When a CME collides with Earth's magnetic field, it can cause geomagnetic storms, leading to disturbances in the magnetosphere and ionosphere. These effects can result in power grid failures, satellite damage, and increased radiation exposure for astronauts. High-speed solar wind. High-speed solar wind streams are associated with coronal holes, regions of the sun's atmosphere where the magnetic field is open to space. These streams can reach speeds of over 800 kilometers per second and can cause geomagnetic storms when they interact with Earth's magnetic field. While typically less intense than CMEs, high-speed solar wind can still have significant effects on satellites and communication systems. Mechanisms of solar storms. Understanding the mechanisms behind solar storms requires insight into the sun's internal processes and its magnetic field dynamics. The sun operates on an approximately 11-year cycle known as the solar cycle, during which solar activity varies from low to high levels. This cycle influences the frequency and intensity of solar storms. Solar activity cycle. The solar cycle consists of periods of solar minimum, low activity, and solar maximum, high activity. During solar maximum, the sun experiences increased sunspot activity, solar flares, and CMEs. The peak of the cycle is marked by a significant increase in the number and intensity of solar storms. Conversely, during solar minimum, these phenomena are less frequent. Magnetic reconnection. One of the key processes that lead to solar storms is magnetic reconnection. This occurs when opposing magnetic field lines in the sun's atmosphere come into contact and rearrange themselves, releasing vast amounts of energy. The energy released during magnetic reconnection can accelerate particles, leading to solar flares and CMEs. This process is critical for understanding how solar storms are initiated and their potential impacts. Plasma dynamics. The sun is composed of plasma, a highly ionized gas consisting of charged particles. The dynamics of this plasma, influenced by magnetic fields and solar rotation, play a crucial role in the formation of solar storms. The movement and interactions of plasma within the sun can create conditions conducive to the development of solar flares and CMEs. The sun's magnetic field. The sun's magnetic field is a complex and dynamic entity that drives solar activity. It is generated by the movement of molten iron and other conductive materials in the sun's outer core, combined with the sun's rotation. This magnetic field extends far beyond the sun, creating the heliosphere, which is the region of space influenced by solar wind. The solar magnetic field is characterized by its polarity, which flips approximately every 11 years as part of the solar cycle. This polarity reversal affects solar activity and the characteristics of solar storms. Understanding the behavior of the sun's magnetic field is essential for predicting solar storms and mitigating their impacts on Earth. Impacts of solar storms. The impacts of solar storms can be widespread and varied. When these storms reach Earth, they can interact with our planet's magnetic field, leading to geomagnetic storms. These storms can have numerous effects, including disruption of communication systems. Solar flares can cause radio blackouts and affect GPS accuracy, disrupting aviation and maritime navigation. Power grid failures. Geomagnetic storms can induce currents in power lines, potentially leading to transformer damage and widespread power outages. Satellite damage. Increased radiation and charged particles can damage satellite electronics, affecting telecommunications, weather forecasting, and navigation systems. Radiation risks to astronauts. During solar storms, astronauts in space are exposed to heightened levels of radiation, increasing the risk of acute radiation sickness and long-term health effects. Conclusion: understanding solar storms is crucial for predicting their effects on Earth and space travel. By studying the mechanisms behind solar flares, CMEs, and high-speed solar wind, scientists can better prepare for the impacts of these events. As our reliance on technology continues to grow, the importance of monitoring and understanding space weather will only increase, underscoring the need for ongoing research in this vital area of study. Through enhanced predictive capabilities and mitigation strategies, we can safeguard our technological infrastructure and ensure the safety of those venturing into space. 3. Mechanisms of solar storms. Understanding the mechanisms of solar storms is essential for predicting their occurrence and potential impacts on Earth and space travel. Solar storms originate from complex interactions within the sun's atmosphere and magnetic field. This section delves into the processes that lead to solar storms, focusing on the solar activity cycle, magnetic reconnection, and plasma dynamics. The solar activity cycle. The solar activity cycle is a fundamental concept in understanding solar storms. This cycle, which lasts approximately 11 years, encompasses periods of varying solar activity, characterized by the number of sunspots, solar flares, and coronal mass ejections, CMEs. Solar minimum and maximum. Solar minimum. This phase is marked by a decrease in solar activity, with fewer sunspots and solar storms. During this time, the sun exhibits a more stable magnetic field, leading to a relatively calm period in terms of space weather. Solar maximum. Conversely, during solar maximum, the sun experiences heightened activity, resulting in numerous sunspots, increased solar flares, and frequent CMEs. This phase is characterized by a more chaotic magnetic environment, which contributes to the occurrence of solar storms. The solar cycle affects not only the frequency of solar storms, but also their intensity. Research has shown that periods of maximum activity are often associated with larger and more powerful solar events. Magnetic reconnection. One of the primary mechanisms driving solar storms is magnetic reconnection. This process occurs when magnetic field lines in the sun's atmosphere interact and rearrange, releasing vast amounts of energy. Understanding magnetic reconnection is crucial for grasping how solar storms form. Formation of magnetic fields. The sun's magnetic fields are generated by the movement of electrically charged plasma within its interior. These fields extend into the solar atmosphere and can become tangled due to the sun's rotation and convection processes. Areas where magnetic fields are particularly strong often correlate with sunspot formation. The reconnection process. Magnetic reconnection occurs when oppositely directed magnetic field lines come into contact. This can happen in regions of high magnetic stress, such as those near sunspots or active regions on the sun's surface. When the magnetic field lines reconnect, they can release energy in the form of heat and kinetic energy. Consequences of magnetic reconnection. The energy released during magnetic reconnection can accelerate charged particles, leading to solar flares and CMEs. This process is critical for understanding how solar storms are initiated and why some storms are more intense than others. The energy released can also create shock waves that propagate through the solar atmosphere, further contributing to solar storm dynamics. Plasma dynamics. The sun is composed of plasma, a state of matter consisting of ionized gas with free-moving charged particles. The dynamics of plasma play a vital role in the development of solar storms. Behavior of solar plasma. Plasma in the sun's atmosphere behaves differently than in solid or liquid states due to its charged nature. The movement of plasma is influenced by magnetic fields, gravitational forces, and thermal energy. This behavior is governed by magnetohydrodynamics, MHD, a field of study that combines fluid dynamics and electromagnetism. Role of convection. The sun's interior undergoes convective processes that transport energy from the core to the surface. This convection contributes to solar activity by generating magnetic fields and influencing the distribution of plasma. The interaction between convective motions and magnetic fields can lead to the emergence of sunspots and active regions, where solar storms are likely to occur. Plasma instabilities. Instabilities within the solar plasma can also contribute to the formation of solar storms. For instance, when magnetic fields become too twisted or stressed, they can lead to explosive events such as solar flares or CMEs. Understanding these instabilities is essential for predicting when and where solar storms will occur. The role of sunspots. Sunspots are temporary phenomena on the sun's surface that serve as indicators of solar activity. These dark spots are regions of intense magnetic activity, and their presence is closely linked to solar storms. Formation of sunspots. Sunspots form when magnetic fields become concentrated in certain areas of the sun's surface, inhibiting convection and cooling the surrounding plasma. This results in dark spots that are cooler than the surrounding areas. The number of sunspots varies throughout the solar cycle. It peaks during solar maximum. Sunspots and solar storms. The presence of sunspots is often associated with increased solar activity. Active regions near sunspots are more likely to produce solar flares and CMEs due to the complex magnetic interactions in these areas. The correlation between sunspot activity and solar storms is a crucial aspect of solar weather forecasting. The heliosphere and solar wind. The heliosphere is the vast region of space influenced by the solar wind, the continuous flow of charged particles emitted by the sun. Understanding the heliosphere is essential for grasping how solar storms interact with Earth and the broader solar system. Structure of the heliosphere. The heliosphere extends far beyond the orbit of Pluto and acts as a protective bubble surrounding the solar system. The solar wind creates a boundary known as the heliopause, where the solar wind pressure balances with the interstellar medium. This region plays a critical role in shielding the solar system from cosmic radiation. Effects of the solar wind. The solar wind carries particles that can interact with Earth's magnetic field, particularly during solar storms. When a CME or high-speed solar wind stream reaches Earth, it can compress the magnetosphere, leading to geomagnetic storms. These storms can induce currents in power lines, disrupt communication systems, and create beautiful auroras. Interplanetary magnetic field, IMF. The solar wind also carries the sun's magnetic field into the heliosphere, creating the interplanetary magnetic field, IMF. The orientation of the IMF plays a crucial role in determining how solar storms affect the Earth. When the IMF is oriented southward, it is more likely to connect with Earth's magnetic field, enhancing the effects of solar storms. Conclusion: the mechanisms of solar storms are complex and multifaceted, involving the interplay of solar activity cycles, magnetic reconnection, plasma dynamics, and the behavior of sunspots. By understanding these processes, scientists can improve their ability to predict solar storms and mitigate their impacts on technology and human activities. As we continue to explore the sun and its effects on space weather, ongoing research will be vital for enhancing our understanding of these dynamic phenomena and safeguarding our technological infrastructure and human health. The study of solar storms not only contributes to our knowledge of the solar system, but also has critical implications for future space exploration and the sustainability of our technology. 4. Effects on Earth. Solar storms have a profound and varied impact on Earth, affecting everything from technological systems to natural phenomena. When charged particles from the sun interact with Earth's magnetic field and atmosphere, they can cause disruptions that have both immediate and long-term implications. This section explores the various effects of solar storms on Earth, including their impact on telecommunications, power grids, satellites, human health, and the environment. 1. Impact on Earth's magnetosphere. The magnetosphere is the region surrounding Earth that is dominated by its magnetic field. It acts as a shield against solar wind and cosmic radiation. Solar storms can significantly influence the magnetosphere, leading to geomagnetic storms that can alter its structure and dynamics. A. Geomagnetic storms. Geomagnetic storms are caused by disturbances in the magnetosphere due to solar wind and solar storms. When a coronal mass ejection, CME, or high-speed solar wind stream interacts with the magnetosphere, it can produce geomagnetic storms of varying intensity. These storms can lead to the following effects. Magnetic field disturbances. Geomagnetic storms can cause fluctuations in Earth's magnetic field, leading to temporary changes in its strength and orientation. This can affect navigation systems that rely on magnetic readings. Auroras. One of the most visually stunning effects of geomagnetic storms is the enhancement of auroras, northern and southern lights. Increased solar activity causes charged particles to collide with atoms in Earth's atmosphere, resulting in spectacular light displays. 2. Effects on telecommunications. Solar storms can disrupt telecommunication systems, particularly those that rely on radio waves and satellite technology. The ionosphere, a layer of the atmosphere that contains charged particles, plays a crucial role in radio communication. Solar storms can cause significant disturbances in this layer, leading to A. Radio blackouts. Solar flares can cause sudden increases in ionization in the ionosphere, leading to radio blackouts. These blackouts can affect high-frequency HF radio communications, which are essential for aviation, maritime, and military operations. The severity of blackouts can vary based on the intensity of the solar flare and the time of day. B. GPS disruptions. Global Positioning System (GPS) technology relies on signals transmitted from satellites to receivers on Earth. Solar storms can increase the density and turbulence of the ionosphere, causing delays and errors in GPS signals. This can lead to inaccuracies in navigation and positioning, impacting transportation and logistics. 3. Risks to power grids. One of the most significant and potentially damaging effects of solar storms is their impact on electrical power grids. Geomagnetic storms can induce geomagnetically induced currents, GICs, in power lines and transformers, leading to a range of issues. A. Transformer damage. GICs can flow through power grids and transformers, causing overheating and damage. In severe cases, this can lead to transformer failures and widespread power outages. The 1989 blackout in Quebec, Canada, serves as a stark reminder of the potential consequences of solar storms on power infrastructure. B. Voltage instability. Solar storms can lead to voltage fluctuations in power grids, making it challenging for operators to maintain stable electricity supply. This can result in cascading failures, where one affected part of the grid causes downstream failures, leading to widespread outages. 4. Satellite damage. Satellites in orbit around Earth are vulnerable to the effects of solar storms. The increased radiation and charged particles can cause various issues for satellite operations. A. Radiation exposure. Satellites are exposed to heightened levels of radiation during solar storms, which can damage sensitive electronic components. This radiation can lead to malfunctions, degradation of materials, and even complete satellite failures. B. Communication disruptions. Solar storms can interfere with satellite communication systems, affecting broadcasting, internet services, and navigation signals. The loss of communication can impact critical services, including emergency response and weather forecasting. 5. Effects on human health. The health risks associated with solar storms primarily affect astronauts and airline crews flying at high altitudes. During solar storms, increased levels of cosmic radiation can pose significant health risks. A. Radiation exposure for astronauts. Astronauts on missions beyond Earth's protective atmosphere are at risk of exposure to harmful radiation during solar storms. This can lead to acute radiation sickness, increased cancer risk, and other long-term health effects. Space agencies, including NASA, closely monitor solar activity to protect astronauts during these events. B. Airline flight risks. Commercial airline flights that travel at high altitudes, particularly those crossing polar regions, may also be at risk during solar storms. Increased radiation exposure can pose health risks for flight crews and passengers. Airlines monitor solar activity to adjust flight paths and minimize exposure during significant solar events. 6. Environmental impact. Solar storms can have various environmental impacts on Earth, affecting both natural phenomena and human activities. A. Enhanced auroras. As previously mentioned, geomagnetic storms lead to enhanced auroras, creating stunning visual displays in the polar regions. However, these displays are also indicators of the energy released during solar storms and their interaction with Earth's atmosphere. B. Weather patterns. While the relationship between solar storms and weather patterns is still a topic of research, some studies suggest that solar activity may influence atmospheric circulation and weather phenomena. Further research is needed to clarify these connections and their implications for climate science. 7. Economic implications. The economic implications of solar storms are significant, given the reliance on technology and infrastructure that can be affected by these events. A. Financial losses. Disruptions to power grids, telecommunications, and satellite operations can lead to substantial financial losses. The costs associated with repairing damaged infrastructure and mitigating risks can run into billions of dollars. B. Preparedness and mitigation costs. Investing in technology to monitor and predict solar storms, as well as implementing protective measures for critical infrastructure, incurs costs. However, these investments are essential for minimizing the risks associated with solar storms and ensuring the resilience of technological systems. Conclusion. The effects of solar storms on Earth are diverse and multifaceted. From disrupting telecommunications and power grids to posing risks to human health and the environment, solar storms present significant challenges that require ongoing research and preparedness. Understanding these effects is crucial for developing mitigation strategies and enhancing our ability to respond to solar storms effectively. As our reliance on technology continues to grow, the need for robust monitoring systems and protective measures becomes increasingly vital to safeguard our infrastructure and ensure the safety of individuals, both on Earth and in space. Continued research and collaboration between scientists, engineers, and policymakers will be essential for addressing the challenges posed by solar storms and harnessing the knowledge gained from studying space weather. 5. Effects on space travel. As humanity ventures further into space, understanding the effects of solar storms on space travel becomes increasingly crucial. Solar storms, primarily driven by solar flares and coronal mass ejections, CMEs, pose significant risks to astronauts, spacecraft, and mission operations. This section explores the various effects of solar storms on space travel, including radiation exposure, spacecraft damage, mission planning, and mitigation strategies. 1. Radiation exposure. One of the most significant threats posed by solar storms is increased radiation exposure. When solar storms occur, they release high-energy particles, including protons and heavy ions, into space. These particles can penetrate spacecraft and pose serious health risks to astronauts. A. Types of radiation. Solar storms primarily emit two types of radiation: solar energetic particles, SEPs. These are high-energy particles released during solar flares and CMEs. SEPs can have energies ranging from tens of MeV, million electron volts, to several GeV, billion electron volts. Their penetration capability allows them to affect both human health and spacecraft systems. Galactic cosmic rays, GCRs. While not exclusively associated with solar storms, GCRs are high-energy particles from outside the solar system. During solar storms, the intensity of GCRs can increase, compounding the radiation exposure risk for astronauts. B. Health risks for astronauts. Astronauts working in low Earth orbit, LEO, and deep space are particularly vulnerable to radiation exposure during solar storms. Acute radiation sickness. High doses of radiation can lead to acute radiation sickness, characterized by symptoms such as nausea, vomiting, and fatigue. While this is more likely during severe solar events, monitoring is essential for all missions. Long-term health effects. Prolonged exposure to space radiation can increase the risk of cancer, cardiovascular diseases, and other long-term health issues. Understanding these risks is vital for mission planning, especially for long-duration missions to destinations like Mars. 2. Spacecraft damage. Solar storms can adversely affect spacecraft systems and components. The high-energy particles and electromagnetic radiation released during these events can lead to various forms of damage. A. Electronic malfunctions. The electronics aboard spacecraft are sensitive to radiation. Solar storms can cause single-event upsets, SEUs. High-energy particles can disrupt the normal operation of electronic circuits, leading to temporary malfunctions or permanent damage. This can affect onboard systems, including navigation, communication, and data processing. Degradation of materials. Prolonged exposure to radiation can degrade materials used in spacecraft, including insulation and structural components. This can compromise the integrity and longevity of the spacecraft. B. Communication disruptions. Solar storms can interfere with communication systems used by spacecraft. The increased ionization in the ionosphere can lead to signal degradation or loss, complicating mission operations. This disruption is particularly concerning for deep space missions where real-time communication is critical. 3. mission planning and operations. The effects of solar storms necessitate careful planning and preparation for space missions. Space agencies must consider solar activity when designing missions and scheduling operations. A. Monitoring solar activity. Continuous monitoring of solar activity is essential for mission planning. Space agencies, such as NASA and ESA, utilize a range of tools and satellites to monitor solar conditions, including solar observatories. Instruments like the Solar Dynamics Observatory, SDO, and the Solar and Heliospheric Observatory, SOHO, provide real-time data on solar flares and CMEs. This information is crucial for predicting solar storm events. Space weather forecasting. Forecasting models use data from solar observatories to predict the intensity and timing of solar storms. This information allows mission planners to adjust schedules and operations accordingly. B. Adjusting flight paths. In response to solar activity, mission planners may need to adjust flight paths for crewed and uncrewed missions. For example, avoiding high radiation regions. During solar storms, spacecraft may be rerouted to avoid regions of high radiation exposure, minimizing risks to astronauts and sensitive equipment. Timing of spacewalks. Spacewalks may be postponed or rescheduled based on solar activity to ensure astronauts' safety. 4. Mitigation strategies. To protect astronauts and spacecraft from the effects of solar storms, space agencies have developed various mitigation strategies. A. Shielding. Physical shielding is one of the primary methods for protecting astronauts and spacecraft from radiation. Various materials can be used to shield against high-energy particles, including aluminum and polyethylene. These materials are commonly used in spacecraft design to provide a barrier against radiation. The thickness and composition of the shielding are critical factors in determining its effectiveness. Water and food supplies. In longer missions, the storage of water and food can provide additional shielding for astronauts. This approach not only offers radiation protection, but also serves as essential supplies for the crew. B. Real-time monitoring and alerts. Implementing real-time monitoring systems that can detect solar storms and provide alerts is vital for mission safety. These systems can help alert astronauts. When a solar storm is detected, alerts can be sent to astronauts, allowing them to take protective measures, such as seeking shelter in shielded areas of the spacecraft. Adjust operations. Ground control can adjust mission operations based on real-time data, ensuring the safety of the crew and the integrity of the mission. 5. Future considerations for space exploration. As humanity aims for deeper space exploration, particularly with missions to Mars and beyond, the implications of solar storms become even more critical. The following considerations are essential for future missions. A. Long-duration missions. Missions to Mars and longer-duration deep space missions will expose astronauts to extended periods of radiation. Understanding the cumulative effects of radiation exposure and developing countermeasures will be essential for the health and safety of the crew. B. Advanced shielding technologies. Research into advanced materials and innovative shielding technologies is necessary to enhance protection against solar radiation. Developing new materials that can effectively shield against high-energy particles will be crucial for future spacecraft design. C. International collaboration. Space weather is a global concern, and international collaboration is vital for monitoring and mitigating the effects of solar storms. Sharing data, resources, and expertise among space agencies can improve prediction capabilities and enhance the safety of space missions worldwide. Conclusion: solar storms pose significant challenges for space travel, affecting astronaut safety, spacecraft integrity, and mission operations. Understanding the risks associated with radiation exposure, communication disruptions, and spacecraft damage is essential for ensuring the success of space missions. As humanity continues to explore beyond Earth, implementing effective monitoring systems, shielding strategies, and collaboration among international space agencies will be crucial for mitigating the impacts of solar storms. 6. Monitoring and prediction. The ability to monitor and predict solar storms is crucial for mitigating their impacts on Earth and ensuring the safety of space missions. As solar activity can vary widely, effective monitoring systems and predictive models are essential for understanding space weather and preparing for its effects. This section explores the tools and technologies used for monitoring solar activity, the methodologies behind prediction, and the importance of early warning systems. 1. Tools for monitoring solar activity. A variety of instruments and satellites are employed to monitor solar activity continuously. These tools provide real-time data on solar phenomena such as solar flares, coronal mass ejections, CMEs, and solar wind dynamics. A. Solar observatories. Solar observatories are specialized facilities equipped to study the sun's behavior. They use various techniques to gather data about solar activity. Ground-based observatories. These facilities, such as the Big Bear Solar Observatory in California and the Mauna Loa Solar Observatory in Hawaii, utilize telescopes and imaging systems to observe the sun's surface and atmosphere. They can capture images of sunspots, solar flares, and other solar phenomena in different wavelengths, including visible light, ultraviolet, and X-rays. Space-based observatories. Satellites like the Solar Dynamics Observatory (SDO) and the Solar and Heliospheric Observatory (SOHO) provide comprehensive data on solar activity from space. These observatories continuously monitor the sun, capturing high-resolution images and data on solar flares, CMEs, and solar wind. B. Magnetometers. Magnetometers are instruments used to measure magnetic fields. They play a vital role in monitoring changes in Earth's magnetosphere and identifying disturbances caused by solar storms. Ground-based magnetometers. These devices are distributed worldwide and measure variations in Earth's magnetic field. By analyzing this data, scientists can detect geomagnetic storms and assess their intensity. Space-based magnetometers. Satellites, such as the European Space Agency Swarm mission, carry magnetometers to monitor magnetic fields in the vicinity of Earth. This data helps scientists understand how solar activity affects the magnetosphere. C. Solar wind monitors. Instruments that measure solar wind parameters are critical for understanding the characteristics of solar storms. Solar wind sensors. Instruments on satellites such as ACE, Advanced Composition Explorer, and DSCOVR, Deep Space Climate Observatory, measure the speed, density, and temperature of solar wind particles. This information is crucial for predicting the arrival and intensity of solar storms at Earth. 2. Prediction methodologies. Predicting solar storms involves analyzing data from various monitoring systems to forecast solar activity and its potential impact on Earth. Several methodologies are utilized in this process. A. Data analysis and modeling. Data from solar observatories and monitoring instruments are analyzed to identify patterns and trends in solar activity. Statistical models. Historical data on solar activity is used to develop statistical models that can predict future solar events based on previous occurrences. These models often consider the solar cycle and the correlation between sunspot activity and solar storms. Numerical simulations. Advanced computer simulations model the behavior of solar plasma and magnetic fields. These simulations help scientists understand how solar storms evolve and predict their potential impacts on Earth. They take into account various factors, including solar rotation, magnetic reconnection, and plasma dynamics. B. Machine learning techniques. Recent advancements in machine learning and artificial intelligence have enhanced the ability to predict solar storms. Pattern recognition. Machine learning algorithms can analyze vast amounts of data from solar observatories to identify patterns associated with solar flares and CMEs. These algorithms can improve prediction accuracy by recognizing subtle signals that may precede solar events. Real-time forecasting. Machine learning models can provide real-time forecasting of solar activity, allowing for quicker responses to impending solar storms. These models can continuously update predictions as new data becomes available. 3. Early warning systems. Early warning systems are essential for disseminating information about solar storms and their potential impacts. These systems are designed to provide timely alerts to relevant stakeholders, including government agencies, power grid operators, and space agencies. Alert mechanisms. Early warning systems utilize various communication channels to alert stakeholders about solar storm activity. Public alerts. National and international space weather agencies, such as NOAA's Space Weather Prediction Center, SWPC, and ESA's Space Weather Coordination Center, SWCC, issue alerts and advisories about solar storms. These alerts are disseminated through websites, social media, and dedicated notification systems. Direct notifications. Critical infrastructure operators, including power companies and satellite operators, receive direct notifications of solar storm activity. This communication allows them to take preventive measures and protect their systems. B. Response protocols. Having established response protocols is essential for mitigating the effects of solar storms. Preparedness plans. Organizations should develop preparedness plans that outline procedures to follow during solar storm events. This may include rerouting satellites, adjusting power grid operations, and notifying personnel of safety measures. Training and drills. Regular training and drills help ensure that personnel are familiar with response protocols and can act swiftly during solar storm events. Collaborating with multiple stakeholders can enhance overall preparedness. 4. International collaboration. Given the global nature of space weather, international collaboration is vital for effective monitoring and prediction. A. Data sharing. Collaboration between countries and space agencies facilitates data sharing, enabling more comprehensive monitoring of solar activity. Organizations such as the International Space Weather Initiative, ISWI, promote global cooperation in space weather research and monitoring. Joint research efforts. Joint research initiatives involving multiple countries can enhance our understanding of solar storms and improve prediction methodologies. Collaborative efforts can lead to the development of advanced modeling techniques and innovative technologies for monitoring solar activity. 5. Challenges in monitoring and prediction. Despite advancements in monitoring and prediction techniques, several challenges remain. A. Predictive limitations. While models have improved, accurately predicting the timing and intensity of solar storms remains a complex task. Solar activity is influenced by numerous variables, making it challenging to provide precise forecasts. B. Data gaps. Data gaps can occur due to instrument limitations or satellite malfunctions. Ensuring continuous and reliable data collection is essential for accurate monitoring and prediction. C. Public awareness. Increasing public awareness of space weather and its potential impacts is crucial for preparedness. Efforts should be made to educate the public and stakeholders about solar storms and the importance of monitoring systems. Conclusion. Monitoring and predicting solar storms are critical components of managing the effects of space weather on Earth and space travel. Utilizing a combination of observational tools, data analysis methodologies, and early warning systems allows scientists to understand solar activity and provide timely alerts. International collaboration plays a vital role in enhancing monitoring capabilities and improving prediction accuracy. Despite the challenges that remain, ongoing research and technological advancements will continue to enhance our ability to forecast solar storms and mitigate their impacts. ensuring the safety of technological systems and human activities in space. Space weather. How solar storms affect Earth and space travel. 7. Conclusion. In recent years, the understanding of space weather, particularly solar storms, has become increasingly vital as humanity ventures further into space and relies more heavily on technology. Solar storms, driven by solar flares and coronal mass ejections, CMEs, pose significant risks, not only to astronauts and spacecraft, but also to critical infrastructure on Earth. The impacts of these solar events are far-reaching, affecting telecommunications, power grids, and even human health. This report has explored the multifaceted nature of solar storms, their mechanisms, effects, and the importance of monitoring and prediction systems. Understanding solar storms. Solar storms are complex phenomena resulting from the sun's magnetic activity and the dynamics of its plasma. The solar activity cycle, characterized by periods of solar minimum and maximum, influences the frequency and intensity of solar storms. Magnetic reconnection plays a crucial role in the initiation of solar flares and CMEs, while the behavior of solar plasma contributes to the overall dynamics of these events. Understanding these mechanisms is essential for predicting solar storms and mitigating their impacts. Effects on Earth. The effects of solar storms on Earth are diverse and can lead to significant disruptions. Geomagnetic storms can induce currents in power grids, causing transformer damage and widespread outages, as seen in historical events like the Quebec blackout of 1989. Telecommunication systems, including radio and GPS, are vulnerable to solar storm-induced disturbances, disrupting critical services. Additionally, the health risks associated with increased radiation exposure during solar storms pose challenges for astronauts and airline crews. The environmental impacts, such as enhanced auroras, also serve as reminders of the sun's influence on our planet. Effects on space travel. As space exploration advances, the risks associated with solar storms become more pronounced. Radiation exposure is a primary concern for astronauts, who may face acute health risks during solar events. Spacecraft are also vulnerable to damage from high-energy particles, leading to potential mission failures. Effective mission planning and operational adjustments are necessary to minimize risks, and real-time monitoring of solar activity is essential for timely decision-making. Monitoring and prediction. The ability to monitor and predict solar storms is critical for safeguarding technology and human activities. A range of tools, including solar observatories, magnetometers, and solar wind monitors, provide essential data on solar activity. Advanced prediction methodologies, including statistical models and machine learning techniques, enhance our ability to forecast solar storms. Early warning systems are vital for disseminating information and enabling effective responses to solar events. International collaboration in monitoring and research efforts further strengthens our understanding of space weather. The path forward. Looking ahead, the challenges posed by solar storms underscore the need for continued research and innovation in the field of space weather. As humanity prepares for more ambitious missions, including potential crewed missions to Mars, understanding and mitigating the effects of solar storms will be paramount. Investments in advanced shielding technologies, improved predictive models, and robust monitoring systems are essential to ensure the safety of astronauts and the integrity of space missions. Public awareness and preparedness are also crucial components of addressing the impacts of solar storms. Educating stakeholders and the general public about the risks associated with solar activity can foster a culture of preparedness, enabling timely and effective responses to solar events. Conclusion. In conclusion, the study of solar storms and their effects is not just an academic pursuit. It has practical implications for our technological infrastructure and the safety of human space exploration. As we continue to expand our presence in space and rely more on technology, understanding the dynamics of solar storms will be vital for safeguarding our systems and ensuring the success of future missions. The ongoing collaboration between scientists, engineers, and policymakers will be essential in addressing the challenges posed by solar storms and enhancing our resilience against space weather phenomena. By investing in research, monitoring, and public education, we can better prepare for the inevitable effects of solar storms and harness the knowledge gained from studying space weather for the benefit of all. Thank you for watching. We hope you enjoyed today's video. If you did, don't forget to hit that like button and subscribe to our channel for more exciting content. Your support means the world to us. We can't wait to see you back here for our next adventure. If you have any feedback or ideas for future videos, drop them in the comments below. Until next time, take care and stay awesome. See you soon.